Okay, so today we're going to review the topics for exam number 4. And first, some general information on the exam. The same format with 20 multiple choice questions, followed by 5 or 6 short answer questions. They'll be of the same types you've seen before: predict the products, provide the reagents, draw mechanisms, as well as synthesis problem. In this section of the class, the synthesis has been different. The only real multi-step synthesis we've gone through has been peptide synthesis, so it shouldn't be giving anything away to let you know that your synthesis problem will be focused on peptide synthesis. And we'll talk more about that when we go through chapter 26. And then we haven't seen them as much recently, but earlier in the class we had questions where we asked you to describe the name the function of a molecule and then describe how its structural features enabled it to perform that function. And so because we've talked extensively about that in recent chapters, you can expect to see a couple of questions of that nature. And I'll highlight the molecules where we connected their structure to their function as we go through the review. So let's find some chalk here. So chapter 26, amino acids and proteins. So we started off in this chapter focusing on the amino acids. And we told you that you do need to memorize the names, the structures, and the 3-letter codes. So our criteria for asking you to memorize information was we just asked you to memorize the structures of the biologically important compounds. And since all 20 of the common amino acids are very important, then we asked you to do that. But we gave you some mnemonic devices. There's that video, that music video you can take a look at on Learning Suite that has some clever mnemonic devices. And just the names themselves, such as the connection between alanine and phenylalanine, asparagine and aspartic acid. Those give you opportunities to memorize those names and structures. So flashcards are helpful for this purpose. Another aspect of amino acid chemistry is the stereochemistry. So being able to correctly draw the naturally occurring enantiomer of amino acids. And just remember that the L is the designation for the natural enantiomer, and L is S except for cysteine. Remember that and cysteine looks the same as all the other amino acids. It's not the opposite configuration. It's just a quirk of the R and S assignment methodology with the sulfur in the side chain giving that atom a higher priority than others. So the priority of the groups is switched, but the actual orientation is the same with cysteine as it is with the other amino acids. So then we talked about the acid-base properties of amino acids. And in this section, a key skill is knowing which form of the amino acid is going to dominate at a given pH. And then there's also the isoelectric point, P sub I. You should know the definition of the isoelectric point and also know how to calculate the isoelectric point. And which pKa values you average depends on whether, of course, if it only has 2 pKa values, that's easy. But if it has a side chain pKa, it depends on if that's an acidic or a basic functional group. So we went over in class a procedure for determining which 2 of the 3 pKa values you would use to determine the isoelectric point. And then there was a titration curve. It wasn't in our textbook, it was from a different textbook, but we went over this titration curve in class. And I would suggest reviewing that because looking at the titration curve can help you understand which version of the amino acid would dominate at a given pH, whether it's the zwitterion, the conjugate acid of the zwitterion, or the conjugate base of the zwitterion. So that titration curve figure was very, very helpful. So then we moved on to discuss the synthesis of amino acids. And there were some methods that we discussed. There were 3 methods we discussed, which are based on chemistry that we've already learned in class. We had the SN2 reactions of alpha halo carboxylic acids. So we could react those molecules with ammonia as a nucleophile. And then because of the inductive effect, that alkylation product would be less reactive than ammonia. And so it's an alkylation of ammonia that stops at monoalkylation. So that works well. We talked about diethyl acetamidomalonate. This is a version of the malonic ester. So it's a version of the malonic ester synthesis, but having a protected amine attached. So the final product that you generate is an amino acid from that version of the malonic ester synthesis. And then we had the Strecker synthesis. The starting material in the Strecker synthesis is an aldehyde. And you react that aldehyde to generate an aminonitrile, an alpha aminonitrile intermediate, similar. So it's kind of a relative of a halohydrin or a cyanohydrin species. Sorry, it's a relative of a cyanohydrin. But you start with an aldehyde, and then you make that alpha aminonitrile intermediate, and the nitrile you can hydrolyze to the carboxylic acid. So those were our 3. There are lots of ways to synthesize amino acids, but those are the 3 that we talked about in class. We mentioned that all 3 of these methods are going to give you racemic products. We told you that this one here with the SN2 could give you a single enantiomer, but it's very difficult to generate an alpha halo carboxylic acid as a single enantiomer. So usually this is racemic, and the product is racemic. So we talked about resolution. Resolution is the process of separating the enantiomers. And because we cannot separate enantiomers directly, we have to do it in an indirect fashion by converting those enantiomers into diastereomers, separating the diastereomers, and then converting them back into the individual enantiomers once they're separated. And we talked about the process that we go through to do that. So you should be familiar enough with that process to describe that process. There was a special type, a subtype of resolution, kinetic resolution. That was where we subjected our mixture of enantiomers to a reaction that would be faster with one enantiomer than the other. That requires a chiral catalyst. And so the example we gave you in the book involved an enzyme catalyzed process that would react with L amino acids much, much faster than D amino acids. Okay? And so this is nice because it's easy to separate the products because they're not even isomers of each other. You have one enantiomer that undergoes a reaction into a different compound and one that doesn't react at all. Okay? And then we briefly mentioned enantioselective synthesis of amino acids. We talked about enantioselective hydrogenation of an alkene to generate an amino acid. You don't need to know anything specific about this particular enantioselective reaction, but each time we talk about an enantioselective reaction in class, we just go back to the general principles behind enantioselective reactions, which is that the only way to have to get a major enantiomer and a minor enantiomer is to have transition states of differing energies leading to those enantiomers, so that one enantiomer is formed fast, the other enantiomer is formed slow. And this is accomplished by using a single enantiomer of a chiral catalyst. And because you have a single enantiomer of the chiral catalyst, the transition states leading to each enantiomer of the product are diastereomers of each other. So if you remember that general principle, that's the take-home message each time we talk about enantioselective synthesis in class. So after we had discussed synthesis of amino acids, we moved on to a discussion of peptides and their structures. We started with the peptide bond. That's just another name for an amide bond. And we talked about how there were two conformations. We have the S-trans and the S-cis. So you should recognize that. S-trans, lower in energy in most cases than S-cis. And then recognizing that the amide bond or the peptide bond is planar because of the resonance. It's a planar bond, but because peptides are polyamides, you have rotation in between the planes of each amide bond. You have twisting about the bonds to the alpha carbons of our amino acids. And so you have twisting between the planes of those amides, and that's what creates such a diversity of three-dimensional structure in peptides. Okay, we skipped peptide sequencing, so remember that you can skip over that. You don't need to study that for exam number 4, and that information rarely shows up on an ACS final, so you can probably skip it in studying for the final as well. But then we went on to peptide synthesis. And our discussion of peptide synthesis focused on protecting groups. So a peptide synthesis problem is going to be different from other synthesis problems we've had. You might think it's easier, so in many cases, than other synthesis problems we've had. If you remember the material we learned on peptide synthesis, there will be no mystery in terms of the types of steps you're going to be required to use. You're going to have to protect certain functional groups. You're going to have to form amide bonds. And then you're going to have to deprotect functional groups. And sometimes you'll want to deprotect one functional group. Sometimes you'll want to deprotect both functional groups. And so you have to understand the protecting groups, their structures, how to install those protecting groups, how to remove those protecting groups. And we taught you more than the book did on this subject, so you'll want to go back and review this so that you understand more than just what is in the textbook in regards to protecting groups. So we paired the Bach group and the tert-butyl ester. So remember that all of our nitrogen protecting groups that we use are carbamates. Those are designed to lose carbon dioxide in the deprotection process to make that favorable. And all of our acid protecting groups are just esters. So we pair up the Bach and the tert-butyl ester because those can be cleaved with HCl, TFA, or HBr. Okay. And then we have the FMOC carbamate, and we can pair that with the methyl ester. And in this case, we can use piperidine. That's a tertiary amine. I'll just abbreviate that here on the board. Piperidine will cleave just the FMOC. That wouldn't cleave a methyl ester. But these protecting groups are put together because you can use a stronger base hydroxide. That would hydrolyze our methyl ester, and that would also cleave an FMOC group. So if you wanted to take both of these off, you would use a base strong enough to cleave the methyl ester that would also cleave your FMOC. Okay? And then our final pairing of protecting groups is the CBZ group and the benzyl ester. And where we've used these abbreviations, you should know the structures behind those abbreviations as well. So if we ask you to, I shouldn't say if, I've already basically told you we'll ask you to synthesize a peptide. But as we ask you to synthesize a peptide, we will ask you to draw out structures once to show that you know those structures. And then after you've drawn the structures once, you can use abbreviations both for amino acids and for protecting groups. Okay. So the CBZ and the benzyl ester, those are cleaved using hydrogen and palladium carbon. And then you can also use HBr. So that allows you to cleave these groups as well as a Bach or a tert-butyl ester. So HBr is a useful method. You can also use hydroxide for the ester, the benzyl ester, but not the CBZ. The CBZ is not cleaved using hydroxide. So we discussed the mechanisms of the deprotection reactions, the formation of either tertiary carbocations in the case of Bach or tert-butyl ester, the formation of benzyl carbocations in the case of CBZ and benzyl ester. We didn't talk about the mechanism for the hydrogenation. We did cover the mechanism of FMOC deprotection. That's a neat mechanism with an aromatic conjugate base. So you should be familiar with those mechanisms as well. Okay. And then an important skill for peptide synthesis is knowing when it is advantageous to remove just one of the two protecting groups versus when you would want to cleave both protecting groups simultaneously. Typically, when we grade synthesis problems, we assign full credit to the most efficient ways of making compounds. And if you come up with a route that works but is less efficient, it's usually going to get most of the credit but not all of the credit. So you'll want to know under what circumstances you would remove just one protecting group versus wanting to remove both. Then we talked about solid phase peptide synthesis. And here, you want to understand the concept of how it is done. And you want to understand the advantages as well as the disadvantages. We said that it streamlines the purification, so that usually accelerates the process. But we did say that that final purification is quite difficult because of all the impurities that are generated, the byproducts generated at each step. And we also said that you have to use excess amounts of those individual amino acids. And if you spent a lot of time and energy preparing those individual amino acids, then that becomes a problem to have to waste some of them. Okay? All right, once we are done with peptide synthesis, we then went into protein structure. And in the area of protein structure, we had 4 categories: primary, secondary, tertiary, and quaternary. So you should be familiar with these. Our most important secondary structures are the alpha helix and the beta sheet. So you should be familiar with those. In general, the types of amino acids you would see or not see in those cases. And then tertiary and quaternary structure, we talked about the types of non-covalent forces that would be involved in those cases. Disulfide bonds are a covalent bond that are involved in tertiary as well as quaternary structures. And there's a couple of figures in your book that summarize this very nicely that we showed in class as well. Uh, uh, Electrostatic attractions or salt bridges, hydrogen bonds, disulfide bonds, a lot of different features involved in these types of structures. I grabbed the wrong paper here. So, and then we talked about some categories of proteins. We had fibrous proteins. Those are the proteins that are insoluble, that form fibers. And alpha keratin was the example that we went over in class. In conjunction with alpha keratin, we talked about the chemistry of a perm and how disulfide bonds play a role in that, the breaking of them, the reforming of them. And then we talked about globular proteins. Our other category are water-soluble proteins. And so those have different roles in nature than our fibrous proteins. And then our examples there that we went over were myoglobin and hemoglobin. Myoglobin and hemoglobin. And there was some vocabulary that we learned in conjunction with these proteins. They're an example of conjugated proteins, meaning they have a protein portion made up of amino acids covalently bonded to a non-protein portion, and we referred to that group as the prosthetic group. And the one that we have in myoglobin and hemoglobin is the heme group. So just knowing the definitions of these terms is important. All right, so that is it for chapter 26. So we'll go ahead and erase the board if we can find the erasers here and get back to you. Okay, so chapter 27, carbohydrates. We started out with just basics in terms of structures, how we draw carbohydrates and classifying them. We showed you how to draw Fisher projections. And so a few skills we need to do in regards with Fisher projections. You should be able to look at a stereocenter in a Fisher projection and determine if it is R or S. You should be able to look at a monosaccharide in a Fisher projection and determine if it is a D sugar or an L sugar. You should be able to look at a Fisher projection and convert that Fisher projection to cyclic representations of sugars, which would either be the Hayworth projection or a chair drawing. And we went over all of those in class. Of course, you should be able to go the reverse direction as well, converting these cyclic versions of our monosaccharides back into an acyclic Fisher projection. So our two types of carbohydrates we learned about were aldoses, the ones with aldehydes, And then there were four aldoses that we asked you to memorize the structures of. And the names, we only asked you to memorize the ones that were important in nature. We have ribose, which is the only pentose that we asked you to learn. And then we have glucose, mannose, and galactose, our three hexoses, aldohexoses, that we asked you to memorize. And of course, mannose and galactose are just epimers of glucose. So memorizing them, as long as you know the structure of glucose, it's pretty straightforward to know those other structures. And then ketoses, there was only one ketose that's important in nature, and that is fructose. And fructose, of course, is related to glucose as well. It has the same configuration at all of its stereocenters that glucose has. So we talked about the cyclic hemiacetal forms of these sugars. That is the form that dominates at equilibrium when you dissolve a sugar in water. And so we have anomers, right? The configuration, we have different anomers or epimers at the anomeric carbon, so some vocabulary that we learned. And then we used the alpha and beta nomenclature to distinguish between those anomers, so you should be able to apply the alpha and beta nomenclature. Alpha having the anomeric OH trans to the primary alcohol at C5, and then beta having the anomeric OH cis to that CH2OH group. Okay. And then, of course, there are two types of cyclic hemiacetals. We have the pyranose, being the six-membered rings. So those are the ones we see most frequently. But then we also have the furanose, the five-membered rings. And we see the furanoses most commonly with ketoses, such as fructose. Even though fructose can form a pyranose, and the pyranose is the major, it's not by much. The cyclic hemiacetal of fructose that's relevant in nature is the furanose. And the same thing goes for our pentoses, such as ribose, as well as deoxyribose. In nature, those furanose forms are quite relevant. Okay, so then we moved on to reactions of monosaccharides. And as for pretty much all the reactions in this section of the class, these are just variations or examples of reactions we've already studied. So we talked about glycoside formation, how to make a glycoside from a monosaccharide, react it with an alcohol and an acid such as HCl. Some key features about this reaction. We obtain mixtures of anomers from a glycoside reaction. We form that resonance stabilized cation intermediate that then gets attacked by the alcohol from either face. This is a reversible process. So we are able to hydrolyze glycosides if we treat them with aqueous acid. And then another thing that's important to understand about glycosides is glycosides do not undergo mutarotation. Mutarotation is an important vocabulary word from this chapter, and glycosides do not undergo mutarotation. Okay. We then talked about something that was not in the chapter, but came up in one of the homework problems at the end of the chapter. And that is the reaction of monosaccharides with strong base, such as hydroxide. We talked about how this can cause epimerization, right, or the formation of epimers. If we treat an aldose with strong base, we're going to get a mixture of C2 epimers, so we get glucose and mannose. And then we also can have isomerization. We can isomerize our aldoses to a ketose, so glucose or mannose will also isomerize to fructose in the presence of a strong base. And we went over those mechanisms in class, so you should be familiar with those. This is the reason why we cannot make ethers from monosaccharides using the typical Williamson etherification reaction. So the etherification of monosaccharides is different. Etherification. I used to be a good speller, but we have to use silver oxide. Usually we're making methyl ethers, so we use iodomethane in the process. And we showed you a mechanism for this reaction that was different from what was described in the book, using the silver oxide as a Lewis acid. So make sure you understand that mechanism that we went over in class. It is the correct one. Then we talked about esterification, making esters from monosaccharides. And that's just the same as making esters from any other alcohol. We use either an acid chloride or an anhydride, and we use pyridine as a weak base for that reaction. Okay, reduction. We use sodium borohydride to reduce the aldehyde of an aldose or the ketone of a ketose. And the product is referred to as an alditol. And this is an important reaction because when applied to an aldose, it gives us a product that has two of the same functional group on each end of the chain. And sometimes that's going to be chiral, and other times it's going to be meso, depending on the monosaccharide that we used. So this is a reaction that can be used to distinguish between monosaccharides if one would give a chiral product and one would give a meso product. Okay. Then we had oxidations. And there were two oxidations we focused on. The bromine and water. That oxidation gives us an alderic acid, I believe. I wrote that too small in my notes to be able to read. No, that's an aldonic acid. I'm glad I looked at that with my reading glasses. I always get those mixed up. Aldonic acid, so that's the compound where you have an aldehyde, or you oxidize the aldehyde to a carboxylic acid, but the primary alcohol remains unoxidized. So you have a carboxylic acid at one end of the chain and an alcohol, primary alcohol, at the other end of the chain. And that is also done with Tollens reagent, Benedict's reagent. And so this reaction is what gives us the definition of reducing sugar. A reducing sugar being a carbohydrate that can be oxidized with Tollens reagent, Benedict's reagent, bromine, and water. So it would be a sugar that has either an aldehyde or is in equilibrium with an aldehyde. Okay. And then our other oxidation that we have is the nitric acid in water. And that gives us the alderic acid. That's the product where we have a carboxylic acid at both ends of the chain, because this oxidant will oxidize both aldehydes and primary alcohols, but not secondary alcohols. So this is comparable to the sodium borohydride reduction because it gives us two of the same functional group at each end of the chain. So in some cases, will give us a chiral product. In other cases, will give us a meso product. Okay? So those are our redox reactions of monosaccharides. Then we had a couple of processes, three-step processes that we discussed. The Voll degradation was one of them. Okay, so you should know the reagents and the conditions for this reaction. We form the degradation means that we are removing a carbon from our monosaccharide. We're doing so through a cyanohydrin intermediate. And then one key thing to remember about the Voll degradation is that because C2 gets turned into C1 in the new monosaccharide, a pair of C2 epimers will give the same product in a Voll degradation. And then we have the opposite process, the Kiliani-Fischer synthesis, a three-step process that also goes through a cyanohydrin intermediate, but we use that intermediate to add a carbon to the chain. And so in that case, C1 of the original sugar becomes C2 of the new sugars, and we generate a pair of C2 epimers in a Kiliani-Fischer synthesis. Okay, so in both cases, we need to know the reagents. We went over mechanisms. Some of them were reactions we already knew. Some were related to reactions we already knew. Then we talked about, this was not in our textbook. It used to be in our textbook, Fischer's proof of the structure of glucose. And so the important thing to know there, don't memorize the proof, but just understand the concepts. Understand how he was able to use chemistry, use chemical reactions in conjunction with whether or not compounds would be chiral or meso compounds to determine the structure of glucose. And you saw some of that on the take-home quiz. There was a problem incorporating some of those principles. Okay, so that concluded the section on monosaccharides. Then we talked about disaccharides. And the important things to understand with disaccharides are the glycoside bond nomenclature. So how we refer to the location of the glycoside bonds. So which alcohols are involved in the glycoside bonds, as well as the stereochemistry of the glycoside bond, whether it's alpha or beta. So understanding that glycoside bond nomenclature, and then understanding if being able to look at a structure of a disaccharide and determining if it is a reducing sugar or not a reducing sugar. Those are the important things to note with disaccharides. But you don't need to memorize specific disaccharides, just be able to understand those concepts. Then with polysaccharides, in this section, what you want to understand is the connection between structure and function. So cellulose and amylose are the molecules that we focused on primarily in this section. And so you should know cellulose has the beta-1,4 prime glycosides. Amylose has the alpha-1,4 prime glycosides. And that gives these molecules different shapes. And those different shapes are key to their different functions. It makes cellulose insoluble in forming fibers. It makes amylose soluble and forming these coils. And so connecting those structures to the functions is important with those polysaccharides. There's a couple of other related polysaccharides you should be familiar with. Amylopectin I remember amylopectin has branches, so it's like amylose with branches off of it. Okay, and we talked about why those branches are important. And then we had an even more branched form of amylopectin, and that was known as glycogen. Okay, so just knowing these names, amylose, amylopectin, and glycogen, and how they're related will be helpful. Then we talked about amino sugars. Basically, just being able to recognize the structure of an amino sugar is the skill that you would want to have here. And then there was a polysaccharide that had an amino sugar in it, chitin, which is a relative of cellulose, a similar structure to cellulose. Then we had N-glycosides. So being able to recognize an N-glycoside, as well as knowing how to synthesize an N-glycoside. We showed you how to do that. You just use an amine and a mild acid to make N-glycosides. And then subsets of N-glycosides, we had nucleosides, and then we had nucleotides. So the nucleotides have a phosphate hooked on to the primary alcohol, whereas the nucleosides are just the primary alcohol. That's just the N-glycoside of the bases used in the basic heterocycles used in DNA and RNA with your ribose or your deoxyribose. So just being able to recognize these, knowing the difference in structure between a nucleoside and a nucleotide would be the important thing here. And then we finished the chapter with a discussion of glycolysis. This was also something that was not in the book, but glycolysis is the catabolism of glucose. We defined the word catabolism, breaking down a larger molecule into smaller, simpler molecules, and releasing energy in the process, or being able to store energy in certain molecules as a result of that process. So you don't have to memorize the cycle. I don't want you to memorize the cycle. You're not going to be asked to reproduce the cycle. But you should understand the cycle and be familiar enough with the concepts and the individual reactions. Being familiar enough with the individual reactions that if you're given a starting material for a step, that you would be able to draw the product of that step. Okay. So again, don't memorize the cycle, but if you're given, be familiar enough with it that if you're given a starting material, you could be able to draw a product, and you should be able to understand the basic concepts underlying glycolysis. Okay, and that's the end of carbohydrates. So we'll take a break to erase the board and come back with lipids. Okay, so chapter 28 is lipids. And as I write this up here, I should mention that chapters 26 and 27 are longer than 28 and 31. We spent more time on those two chapters. And as a result, there will be more questions on those two chapters. So there's more than half of the exam is 26 and 27, and less than half is 28 and 31. But there's plenty of 28 and 31. Do not ignore those chapters. If you ignore those chapters, you will be disappointed. So some general things with lipids. So we need to be able to classify. So you need to be able to look at a structure of a lipid and determine what type of lipid it is. Okay. And then in cases where we connected the structure of a lipid to its function, you should be able to explain that in your own words. And And we'll go over that as we go through this section here. So we put our lipids in two broad categories. The first one was the hydrolyzable lipids, those which can react with acid or base, aqueous acid or base, and be cleaved into smaller molecules. The first ones we talked about were the waxes, very simple compounds, the easiest to identify, hopefully. And with waxes, we did connect the structure to the function, so that's something you should be able to explain on your own. Then we talked about triacylglycerols. So here you should be able to identify the structures again. Triacylglycerols can be made up of saturated fatty acids or unsaturated fatty acids, and that's going to lead to, sorry, broke the chalk, differences in properties of those molecules in terms of melting points. So understanding those differences, the saturated ones are referred to as fats, the unsaturated ones are referred to as oils. And then another catabolism pathway that we mentioned that was not in the book, fatty acid beta oxidation. Where we made thioesters from our fatty acids. We would oxidize at the beta carbon, and then that would allow us to perform a retroclaisen reaction to break those molecules off into two carbon pieces, acetyl coenzyme A, and a new fatty acid or a new thioester with two less carbons that could then go through the cycle again. So we can degrade our fatty acids into acetyl coenzyme A molecules that undergo further catabolism to generate energy. But we talked about how energy is generated and stored from this fatty acid beta oxidation pathway. So this was comparable to our discussion of glycolysis. You don't need to memorize the entire pathway, but you should be familiar enough with it to be able to predict products of individual steps and to understand those general concepts that I just summarized. Okay. Our next category of hydrolyzable lipids was our phospholipids. And our phospholipids have two categories. We have our phosphoacylglycerols. Those are the more common ones. Most of the phospholipids we discussed were phosphoacylglycerols. Here we connected the structure to the function. Their structures allow them to have these polar head groups and these nonpolar tails, allowing them to assemble into lipid bilayers. So you should be able to explain that. And then we had the sphingomyelins. And with the sphingomyelins, just being able to recognize the structure. We didn't really explain how the structure enables the function with generating the myelin sheaths. Then we had our non-hydrolyzable lipids. And our non-hydrolyzable lipids started with our fat-soluble vitamins. And here, the important ones to focus on are the two where we connected the structure to the function. And that's with vitamin A. That was an earlier process where we discussed how the chemistry of vision is based on how vitamin A plays a role in the chemistry of vision. And then vitamin E, that was also earlier. Vitamin E, being an antioxidant, it is able to donate a hydrogen atom to a radical species, generating a highly resonant stabilized radical that is then much less reactive. So it's therefore able to interrupt harmful radical chain reactions that would cause degradation of unsaturated fatty acids. Okay? All right, and then eicosanoids, our next class of non-hydrolyzable lipids. Here, the key is just being able to recognize the structures. These are derived from arachidonic acid. They have 20 carbons. There were various classes of them. We didn't really study their structures and functions, but just being able to recognize that they fit in this category. Then we had our terpenes. And with terpenes, there are a couple of things that are important. So being able to count the isoprene units. So determining how many isoprene units are present in a terpene. Being able to determine where those isoprene units are connected to each other. So finding the connection points. And then also understanding the biosynthesis of the terpenes. We went over a mechanism for how dimethylallyl is linked together with isopentenyl pyrophosphate to generate geranyl pyrophosphate. So being able to draw that mechanism, being able to understand that biosynthesis process is important. Okay, and then the steroids. Those were our final non-hydrolyzable lipids. So a few key things about steroids. We talked about the trans, anti, trans stereochemistry. The ring fusions are trans. The relationships between each ring fusion are anti. That's not always the case, but that's the most common stereochemistry that we see there with steroids. We talked about the most common steroid, cholesterol. And with cholesterol, we connected its structure to its function. It provides rigidity to cell membranes, and we discussed why its structure is rigid. No ring flipping due to the transdecalins. We talked about the tetracyclization process that occurs in the biosynthesis of steroids. Right? Many of the other steps in the steroid biosynthesis are pretty crazy. We're not really going to expect you to reproduce the crazy sequence of 1-2 shifts that occurs. But the tetracyclization, we did talk about that. We talked about how the stereochemistry in the cyclization of the squalene oxide, that epoxide, the stereochemistry that results is all encoded in the stereochemistry of the double bonds. It's a consequence of the trans stereochemistry of the double bonds combined with the chair-like transition states that we have in the formation of those 6-membered rings. So understanding that, so you should be able to predict the product of one of these types of cyclizations, and also knowing that that cyclization can occur in a flask. It does not require the enzyme in order to occur. And then we went over a bunch of different steroids. That was mostly for your information because these are important molecules. But cholic acid, which is the acid that we make bile salts from, is one of the molecules that we did connect the structure of the molecule to its function. So that's something that you should be able to explain. And that concludes lipids. So we'll erase the board again and then discuss synthetic polymers. All right, chapter 31, synthetic polymers. So the first thing to note in this outline is that we will only cover through section 31.6 for this exam. The material past that is interesting. We are going to mention it in class on Wednesday. Some of it's the most interesting material in the chapter because it's the most relevant, related to issues such as plastic recycling, the formation of plastic waste, which is a huge issue today. But for the exam, and in today's review, we're only going to go through section 31.6. So some general skills related to this chapter that you want to have is to be able to identify the monomer from the repeating unit. If you're given the repeating unit, be able to identify the monomer. We had an iClicker question on that in class. And then vice versa, you should be able to do that in reverse. If you're given the monomer or monomers, you should be able to draw the repeating unit of that polymer. So both of those things are important. So we have our two classes of polymers. We have our chain growth or addition polymers formed by addition reactions repeated. And these are chain reactions. And there are three types of mechanisms, three types of chain reaction mechanisms that can be used to generate these chain growth polymers. We have our radical polymerization, our cationic polymerization, and our anionic polymerization. So you should be able to draw mechanisms for each of these processes. There's an initiator in each of these types of reactions, so you should know the initiators that are used in radical polymerization, cationic polymerization, and anionic polymerization. And then, of course, part of knowing those mechanisms is recognizing that all three of them are going to have an initiation phase, one or two steps, followed by a propagation. That's usually one step repeated over and over again, followed by a termination step. So you'd be able to draw those as part of a mechanism. And then some specific polymers we talked about. Again, it's the ones where we connected the structure to the function. And polyethylene, we did that. So in polyethylene, we talked about the two different types, HDPE versus LDPE. And we talked about how the structures of these molecules allow them to have different functions, allowing HDPE to be used for plastic bottles, milk containers, and LDPE to be used for sandwich bags and so forth. Okay? So being able to explain that, the structure, the connection between structure and function for both of those molecules is important. And then one thing we talked about with anionic polymerization is that it is a living process. So understanding what living polymerization means, that's important. Okay. We learned about copolymers. So understanding the definition of copolymers. We have two types of copolymers. We have random copolymers. We have alternating copolymers. So understanding those and how they differ. Note that one of the copolymers we discussed in class came from a 1,3-diene, and so it would have an alkene remaining in the backbone. And then we talked about epoxides. as monomers in polymerization reactions. We talked about how that makes a polyether that is then going to be soluble in water. So that catches us up with what we talked about through today in class. So just outlining the topics we're going to cover on Monday in class that you'll see on the exam. We'll start off talking about Ziegler-Natta catalysts. So Ziegler-Natta catalysts are metal catalysts, transition metal catalysts that allow us to make HDPE. Okay, so that's how we make polyethylene without branches. And then there are some related catalysts known as metallocene catalysts. We'll discuss their structures, and those can also generate HDPE or an even longer form that we'll talk about in class on Monday. But in conjunction with these metallocene catalysts, there's also some polymer stereochemistry. If we're making polypropylene, for example, which would have a methyl group coming off, or any of our polymers really, that when we have the Z group coming off the chain, that carbon is a stereocenter. And so depending on the pattern that you have of stereochemistry, you can have what's known as an isotactic polymer. An isotactic polymer is going to be chiral. Okay. And then a syndiotactic polymer is going to be a meso compound or achiral. Okay. And based on what we've talked about with enantioselective reactions, it shouldn't be a surprise that if you're going to make an isotactic polymer, you're going to need a chiral catalyst. And if you're going to make a syndiotactic polymer, you're going to need a mesocatalyst. So that's something we're going to talk about on Monday. Then we're going to talk about rubber. Okay. So rubber is going to have an alkene in the backbone. It's going to have a Z-alkene or a cis-alkene in the backbone. A relative of rubber is known as gutta-percha. Gutta-percha has E-alkenes in the backbone. And this difference in alkene stereochemistry causes a profound difference in the properties of these molecules. So these are ones where we're going to connect the structure to the function. So that's something you'll want to pay attention to. We're going to learn about a process known as vulcanization. Sounds exciting. Vulcanization is a way of forming crosslinks in rubber. And so that's going to change the properties of the rubber. So that's something we'll want to understand. It creates a type of polymer known as an elastomer. An elastomer is going to stretch but return to its shape after the force is not applied anymore. So rubber bands, for example, would be elastomers because those are made from vulcanized rubber. Okay. All right, and then we will move on to step growth or condensation polymers. We talked about that a little bit today in class, about what condensation reactions are and how these polymers usually involve two different monomers that each have two functional groups, two of the same functional groups on each end of the molecule. So we can have polyamides. Examples of those, nylon and Kevlar. Just being able to recognize that those are polyamides. We can have polyesters. An interesting thing, so polyesters are going to be less stable than polyamides because esters are more reactive than amides are. And so you can make dissolving sutures from polyesters. We'll talk about how that's done in class. Polyurethanes, those are pretty common. That's a term you might have heard before. So polyurethanes are polymers made from carbamate linkages. We've seen carbamates used as nitrogen protecting groups for amino acids, but they can also be used to link monomers together in polymers. Spandex and actually memory foam mattresses are polyurethanes. Polycarbonates. So most of these you'll just want to recognize their structures. We'll show you what a carbonate is in class and how that linkage can be used in step growth polymers. And then we'll talk about epoxy resins. Epoxy resins are neat because epoxy resins are cross-linked. There's a cross-linking step that's actually done by the consumer. So when you use an epoxy resin, you actually get to do some of the chemistry to make the polymer to get it to harden. And we'll talk about that in class. That's a category of step growth polymer. So that's everything we're going to cover for polymers for the exam. So these are the topics you want to focus on.